For chapter 7, electronic device application. So let's look one of the device, okay, one of the device where we will focus on oscillators, okay. So the best part for chapter 7 is it will not come out, it will not coming out for your final, okay, it will not coming out for your final test, but for chapter 7 you need to do your assignment, okay, ada assignment you need to do. I think it will be group assignment. So what we will cover for chapter 7, we will look the basic operating principle for oscillator. I think any of you that didn't know what is oscillator is, tahu kan? Oscillator is a very basic very basic electrical device for you to detect output signal, for you to look how the output waveform look like, right? So that is oscillator. So in this chapter, we will look how the oscillator works, yeah, how the oscillator operates, yeah. So we will look how the principle, the operating principle, and then oscillator also have feedback. Okay, so we will discuss the principle on which feedback oscillator is based on. Okay, and we will look the operation of RC feedback for oscillators, and ada juga LC. Okay, RC and LC, and then we will discuss as well the relaxation oscillator, or also known as multi-vibrator oscillator. Okay, and we will look also 555 timer. Alright, 555 timer. This is one of the applications, yeah, for oscillator applications. So for today, we will cover only this principle and the feedbacks, yeah. So introduction, what is oscillator? Oscillator is the electronic circuit that produce a periodic waveform. So periodic waveform, you can see that the waveform is uniform, yeah. Periodic waveform with only DC supply voltage as an input. Okay, DC supply voltage as an input. So there's no sinusoidal input is needed. Okay, so there's basically no sinusoidal input is needed for an oscillator. Okay, they only need for the DC supply. Okay, later on we will see, since that there is no input of sinusoidal, how come there is a waveform can be represented at the output of the oscillator later on, yeah. So if the feedback circuit returns the signal out of phase, an inverting amplifier produces the positive feedback, all right. So these are the feedback, yeah. If the feedback of the circuit, okay, returns the signal out of phase, yeah? It means if the signal sometimes will come out as a out of phase, so there's an inverting amplifier, okay, there's an inverting amplifier, okay, produced as a feedback. We have learned the feedback, right? So there's gonna be amplifier will produce as an feedback, okay, to make sure that the signal will be in phase again, yeah. So basically, oscillator can be divided into two parts, which is the sinusoidal oscillator, or also known as feedback oscillator, and then non-sinusoidal, or also known as relaxation oscillator, okay. And relaxation oscillator also known as multi-vibrator oscillator. Okay, dia ada banyak lah the names, yeah. Okay, so these are the basic of the oscillator, yeah. It requires a DC supply DC supply voltage. So this is inside the oscillator, where inside the oscillator is actually have an amplifier and have the feedback, okay. And the output can be in sine wave for the sinusoidal type of oscillator, and also can be as a square wave, okay, for the non-sinusoidal, and can be also as the sawtooth wave, yeah, sawtooth, this one. So this is for the non-sinusoidal. Okay, most people use for the sine wave, okay, sine wave and square wave. I think it's very familiar for you to use during your experiment, okay, or during your research, okay. But it's very rare to use the sawtooth wave, yeah. Okay, so this sinusoidal feedback oscillator, the configuration we're gonna look like this. Okay, so this is the in phase, yeah. When the input signal is in phase, they will use non-inverting amplifier will work okay, non-inverting amplifier will work. And since that non-inverting amplifier, it will not invert this waveform. Okay, the waveform will be apa ya? I don't know what exactly. Yes, exactly as what the input is. Okay, I mean in terms of interval and all those things will be exactly the same as the input. But what this non-inverting amplifier do, it will amplify. Okay, it only will amplify the amplitude of this input signal. Okay, you can see that the input signal will be large. The amplitude will be higher compared to the input signal, and then this will be the output, and there is always a feedback circuit to return this signal. Okay, to return this signal and make it as usual. That's why it will become a periodic. Okay, that's why it will become a periodic cycle like this. Yeah, because there is a feedback circuit to make it oscillates the waveform. Okay, and then for this inverting amplifier, yeah, it will be used when the waveform is out of phase. Yeah, when the waveform is out of phase. Sorry, yeah, the inverting amplifier will invert this signal to make sure it in a phase again, and it also amplify, okay, the signal. Okay, it will make the amplitude higher, and there's, you can see at the output will be same, and since that there is a feedback, there's also this waveform will return again to this input, yeah, since there is a wave feedback, and it will make the waveform oscillates, yeah. So that's why you can see a repetitions of waveform at the using the oscillator. Okay, so this is this sinusoidal or feedback oscillator, how it works. For non-sinusoidal or relaxation oscillator, there is a capacitor here. Okay, so there is a capacitor. So of course, when there is a capacitor, there is a charging and discharging of the capacitor itself. Yeah, so that's why you can see because of the existence of this capacitor, it will make as a time interval. Okay, they are the relation with the time interval. Okay, for the capacitor to charge and discharge. Yeah, and yeah, this is how the configuration. This is the simple configuration looks like. Yeah. So let's look what is the sinusoidal sinusoidal or feedback oscillator. Okay, so the oscillator operate is based on the principle of positive feedback. Okay, always, yeah, feedback oscillator always work in a positive feedback. Okay, and it generates, okay, the outputs will always generate the sine waveform. Okay, the sinusoidal waveform, and that's why it is known as sinusoidal oscillator. Okay, the positive feedback is characterized by the condition wherein a portion of the output voltage of an amplifier is fed back. Okay, this feedback, yeah, will make sure that the output voltage, yeah, the output voltage waveform will feed again. Okay, will fed again, will enter again the input. Okay, will enter again the input of this amplifier. So that is the function of the feedback circuit. All right. So there are two cases for this sinusoidal oscillator. One is in phase, where in phase it will use the non-inverting amplifier, will work, and the other one will be out of phase. Yeah, if out of phase, it means that it will use as inverting amplifier. Right? Some amplifier, the feedback circuit shift the phase 180. Okay. Some amplifier, yeah, for the inverting case, yeah, the feedback will shift 150 phase shift, and some of them will, the feedback, yeah, the feedback here, some of them will feed again the input, exactly as the input, yeah, exactly as the input. For example, in phase, yeah, they will exactly feed again the input as in phase. Okay, because all the waveform is in phase, so the output from the feedback also will be in phase. But for the output phase, out of phase, for the out of phase condition, the feedback, the feedback will input the input of the oscillator waveform. Okay, the waveform will also will have a slightly phase shift. Okay, to make sure that the input of the oscillator will be in phase again. Right. So itulah what is the basically of this feedback. For I think for in phase it's very easy. What will different is the amplifier will just amplify the amplitude, but for the out of phase case, it will this amplifier will invert this waveform to make sure that it will be in phase again, and then it will amplify the amplitudes, and then the feedback circuit also will fit again the input with the phase shift. Will phase shift depending on what is the conditions of the conditions of the out of phase waveform. If the waveform is 150 phase out of phase, so the inverting amplifier will invert 180 phase shift, and the feedback circuit also will will fit 180 phase shift to the input signal again. So next, this is the sinusoidal, the harmonic distortion. Okay, how they will make the harmonic distortion, total harmonic distortion. Okay, 100, okay, square root. Okay, this is just for your information lah, the knowledge. So dk represent what? This d represent what? It represents the ratio of the amplitude. Okay, the ratio of the amplitude of the harmonic. Of the harmonic of the fundamental in Fourier series. So this is based on Fourier series given wave. So for the pure sine wave, okay, for the nicely sine wave, okay, without any noise, the THD will be equals to 0. But if there is a slightly noise, slightly noise like this, the THD will make is depending on the noise. So the bigger percent of THD, it means that the output wave is not a pure sine wave anymore. So if you want to justify the output wave is sine wave or not, it's depending on the THD percentage. 0% means that the output voltage is very nice sine wave. So these are the how the feedback oscillators works. So these are the gain. Okay, these are the amplifier. Okay, so since that this is the gain, we know the gain, how to calculate again. Gain is output voltage over input voltage, right? So for you to get the output voltage, if there is a given the value of gain, it will be A, okay, which is the gain value, the input voltage, the input voltage. So in this case, the input voltage is Vs, which is the source of the signal voltage, and plus with the value of the feedback value voltage. So Vs plus Vf will be the input voltage here. So Vs will be exactly Vs value. Okay, Vf will be the output voltage. This is also another gain. Okay, gain with the value of the feedback here, even though it is a feedback, it is actually a gain. Times with the beta, beta, okay, output will be value of Vf. So you can rewrite this equation. So it will be Vo 1 minus A beta equals to AVS. So from here, you can see the ratio of VO over Vs is equals to A over 1 minus A beta. So usually this value is given to you. You can find this value inside the circuit. So from here, you can calculate the value of output and the value, the ratio between the output and the compared to the source ratio. Okay. So usually, BA, okay, BA is equals to 1. Okay, for an oscillator where the VS value, when the VS value is equals to 0, okay, and A is the real finite number, it means that real number, for example, 10 or usually hundreds, the value is 100. Therefore, okay, you will get 1 minus AB, okay, 1 minus AB is equals to 0. Okay, since that if the Vs is equals to 0, yeah, if the source voltage is equals to 0, 1 minus AB will be equals to 0 as well, right? Will be equals to 0 as well. And A is usually a finite number, okay? I mean exact number, and B as well. All right. So once you get A is equals to 0, 1 minus AB is equals to 0, so it will be the ratio. It will be the ratio will be A over 0. The ratio of output and source will be A over 0, right? So A over 0, we know, yeah. This ratio will give to you, the value will be infinity. Okay, and this infinity means, what is the meaning of this infinity? It means that this oscillator, okay, this oscillator will reach to Barkhausen criteria. Okay, Barkhausen criteria. Later on we will look what is the Barkhausen criteria. Okay, so to reach this Barkhausen criterion, okay, it will make the output value, the output ratio over input, okay, the ratio between output and source is infinity. Okay, so when the output and the source ratio is infinity, so it means that the oscillator is near with the Barkhausen criterion. Okay, so to get this Barkhausen criterion, this Vs should be equals to 0. Okay, Vs should be equals to 0, or this value, yeah, this value, AB value should equals to 1. Okay, so 1 minus 1, it will be 0. Okay, so it will be infinity again, yeah. So there's two conditions to make it as a Barkhausen criterion. Either Vs is equals to 0, or beta A equals to 1. Okay, the value of beta and A equals to 1. So this we're going to reach the Barkhausen criterion. Okay, so there are two conditions to sustain the state of the oscillator. Okay, to make the state of the oscillator creates a nice periodic. Okay, so there are two conditions. First of all, the phase shift around the feedback loop must be effectively 0. Okay, the phase shift here should be 0. So it means that the feedback here, yeah, there is no phase shift between the feedback at the output here and the feedback that goes into input. All right. So this the phase of the waveform is exactly zero phase shift. Yeah? So it means that exactly the input and the output is the same. The voltage gain, okay, the voltage gain around the closed feedback loop must equals to 1, okay, which is A beta just now, A and beta just now should be 1. All right, A beta just now should be 1. All right, or if there is a Vs, kalau ada Vs kat sini, if there is a Vs, the Vs value should be 0. Okay, but if there is no Vs, sometimes the Vs value it's very hard to get 0. Yeah, the source, the value of A and B, AV and B here should be 1. Okay, the value should be 1. Okay, so let's look here, the example here. Yeah, so these are the gain value here is 100. And the beta value here is 0.05. You can see that the value of beta gain is less than 1. Okay, it's less than 1. Okay, later on you can calculate here, yeah. When the input is increased, okay, when the input of this voltage is increased, let's say from here in this condition 0.1, the output will be 10. How we get the output is depending on the, based on this equation, yeah, V output V output is A VI, alright? So VI is 0.1, so 0.1 times 100, you will get 10. So, and this will give you the output value. And the VF, okay, the VF, there is a phase shift. 0.05 means there is a slightly phase shift here, which is 0.0005. So it will make the value of beta gain lesser than 1. Yeah. So in this case, when you change the beta here, yeah, usually the gain is apa? The gain value is uniform, sama, constant. Okay, only the feedback can change. Yeah. So if the feedback, if you increase a little bit, you will get. Okay, if you increase too much, yeah, for example, from 0.005, you increase to 0.1. So it will make the beta A value more than 1. Okay, more than 1, right? So more than 1. So for example, you can from here, so this is the value of input, so this is the value of output, and you will get the value of VF is equals to 1. Yeah, VF is equals to 1, yeah, right? How to get VF? So VF is usually is beta V output. Yeah, how to get VF? Beta V output. Yeah, beta V output. All right. Next, from here, if you increase again the value of beta, you will, for example, slightly increase from here and not too much, yeah, 0.01, you will get the value of beta gain is equals to 1, and you can calculate the value of output, which is A equals to, output is equal to A VI. And here you can calculate the value of feedback voltage, which is the beta VO, right? This is, so you can get all this information. So let's look for the once you with the differentiate, yeah, once you increase the input value, okay, once you increase the input value with this value of gain and beta, you can see that the output, okay, the output is become lesser. Okay, the output become lesser and lesser. So your output waveform will be in periodic, will not be uniform. It will be it will be smaller and smaller like that. All right. Next, when the beta gain is more than 1, what will happen? Okay, you can see that the output voltage is increasing. Okay, increase and increase and increase, uniformly increase. Yeah. And what will happen? It will saturate. Yeah? At one point, the VUTP and VLTP will saturate the output. Yeah, will make that later on your waveform will make like this. Dia akan jadi macam square. Okay, you will not have a nice sine waveform. Okay, if the beta gain more than 1. Okay, next, when the beta gain equals to 1, what will happen? You can see that the output is uniform, always 10, 10, 10, and 10. So you can have a nicely sine waveform. Okay, you will get nicely sine waveform. All right. So up until here, any questions? So from this here, to make sure that you get the nicely periodic sine waveform, you have to make sure that the beta and the gain here will equals to 1. Yeah, equals to 1. Okay, usually the value of gain is 100. Yeah. Many of the oscillator, they use the value of gain is 100. Yeah? And the value of beta we're gonna be fixed, 0.01. But sometimes you can also change the value of gain, 50 or something like that. 50, 10. Right? So up until here, any questions? All right. Okay. All right. So if no questions, I think next week on Tuesday, since that we have no class on Monday, we will look what is the Barkhausen criterion, okay, and then what is the condition, and then we're going to look what is the RC network and the LC network, okay, RC and LC network. Okay, so on the next class also I will explain about the apa assignment. Okay, assignment for you to complete. It will be group assignment if I'm not mistaken. Yeah, so I think it's easier. Okay, so any questions? If there's no, I think we can end the class earlier because we start earlier just now. And yeah, again ya, next week tak ada class. And apa lagi? Yeah, I will confirm about your test too. Dah lupa dah about test. Wait. About your test, so I will inform to you. Hopefully by today. Okay. But in case, just do your revision. Okay, just do your revision. Just prepare with your revision. The worst case, you might have tests on this 10 on the Thursday. Okay, on this Thursday, but it's not confirmed yet. The worst case, just be prepared. Just get ready. Yeah. For your test, it's very easy. It's about DC, BJT, and DC MOSFET. Okay, N channel, and E MOSFET lah. For MOSFET is E MOSFET, N channel also. Okay. Alright.
Sensei.
Yes.
Untuk DC maksudnya tak sampai yang transconductance semua tu pi model tak ada lah.
Pi model, ya betul. Pi model, pi model masuk DC ke? Aku tak ingat lah.
Pi model is AC, right? So
if I'm not mistaken, pi model is AC.
So biasa the DC is only the KVL for like BE loop, BC loop.
Yes. AV
Okay.
loop, yang tu. Okay, so master yourself about this all those loops, yeah. And then apa lagi kalau DC ni sekejap this is my notes for the
Kena draw transfer curve tak?
Okay, transfer curve it's better for you to draw. Okay, it's better for you to draw. In your final also, hari tu ada conflict among the lecturers yang they were going to give mark for you if you draw the transfer curve, but some lecturers say it is basic or it is very common for you to draw transfer curve, so no need to give marks. But for me, my advice is tak kisahlah if you have marks or not by drawing the transfer curve. My advice is always draw transfer curves. Okay. Especially kalau ada theorem, apa nama dia, theorem Thevenin theorem. Okay, especially when there is a Thevenin theorem, please draw the transfer this is transfer curve kan, transfer curve kena lah draw. This is for the graph. What I'm talking is about the circuit yang simplified circuit tu. Okay. So sorry. Dah confused dah dengan transfer curve dengan simplified circuit. Transfer curve kena juga draw. Okay, please look also for how to draw the transfer curve. Okay, tapi tak ada graph.
Dia akan tanya graphical method.
Graphical method no. I mean kalau dia tanya pun they will not ask you to draw the graph. They will give you the graph. Okay, they will give you.
To prepare to like print out the graph so
no. What I mean is they provide you the graph, so you need to know how to read the graph. What information that you can get from the graph. You don't have to print. You don't have to prepare the graph paper. Tak perlu pun. Okay. Sebab nanti susah for you to upload and for you to print kan. So it's quite difficult if any of you don't have graph paper. The graph is provided to you. The transfer curve graph is provided to you. Okay. But what you need to know is how to read the graph. How to get information from the graph. Itu je. You don't have to prepare the graph paper. Okay. Okay tak? Faham ke? And then you also need to, okay, tak perlu prepare graph paper. What you need to do is you need to read the transfer curves graph, and then you also need to Once you draw the graph, I need to look my notes again. And also, yeah, the Thevenin theorem. Please pay attention on the Thevenin theorem too. And then, please look also for the dual supply or single supply. Okay, dual supply or single supply. I think once you get a dual supply, for single supply, no problem. So please pay attention on that too. Yeah, that is for the BJT. Okay, for the BJT. For the MOSFET, for the MOSFET, and then for the MOSFET, for MOSFET, mana? For MOSFET, as I mentioned just now, for MOSFET also, please prepare for the Shockley's equation kan for MOSFET, where it is the one that we used before, which is to Shockley equation mana itu? VGS, okay. I use this slide. VGS minus VGS threshold. Okay. K squared. Okay, so please memorize this equation also. Okay, because this one is very useful if you want to calculate the value of ID kan. Okay, so ingatlah for this equation. I'm not sure if this equation is given or not, so please be prepared. Okay, list of equation. All right, any questions? All right, okay, so if there's no questions, I will end our class here. Ada ke? Ada questions?
Sensei, untuk part A biasa dia tanya teori-teori ya?
Yes, betul. Yes. So for part A, biasalah, what is the threshold, ya? Apa tu N channel, P channel ke, especially for MOSFET kan, we have lots of configurations of MOSFET, J MOSFET, E MOSFET, and then apa lagi for BJT we have configuration between two diodes kan, right? So please prepare also. Yeah, I lupa, because some for the test ada arguable as well, might be open book. So open book, if it is open book, you only can refer on the slide notes that all the slide notes, the class notes that been provided to you, right? Only that, yeah. So if it is in open book questions, open book test, yeah, you can only you can refer to all our notes. So I think should be much easier for you. Alright, so later on hopefully by today, kalau I lupa nak bagi, nak inform, kalau dah let's say lah at dah malam macam tu, dah at 7 or something like that, I forgot to mention to you what about your test, please remind again dalam group WhatsApp tu, because sometimes I lupa because today I have back-to-back meeting. Alright, please please study for your test, be prepared je lah. Okay, any questions later on? No more questions? So no more questions, we can end our class today. So thank you so much. See you next Tuesday, inshallah. All right, thank you.